I'm going to start today's session by describing a fairly simple experiment, but it has some really important results. It's an experiment that I can't physically do right here, right now, but what I will do is I will put a link to another video that's not made by me, it's made by the Institute of Physics. I'll put a link to that video in the description where they actually show you this experiment very, very clearly. So feel free to jump to that. Now, this experiment, basically it's called the gold leaf electroscope, and I'm going to show you what it involves. We have a wooden box, okay, with a glass front on it. There's a little metal rod hanging, and just hanging off this metal rod, there's a very thin film, a very thin foil of gold, okay? It's very, very light, and it's obviously a very good conductor. Now on the top here, we've got a metal plate, which is, for the purposes of showing this experiment, we usually use zinc, and I'll explain why that is a little bit later on. Now, basically what we do is we want to get this whole system here negatively charged. We can do that by bringing a positively charged rod close to it. We would then earth it. Okay, so by bringing the positively charged rod close to it, what it's going to do is it's going to pull all of the electrons up. This becomes positively charged at that point, this bit down here. We're then going to earth it. Extra electrons effectively join the system, and then when we then remove, so we unearth it, we then remove the positively charged rod, and this system will then be left negatively charged, okay? And that's the key thing. We don't need to worry too much at this point about how we physically get it charged, but basically what we need to understand is that we've got a system where we've got this gold leaf electroscope, which is overall negatively charged. Now obviously there are positive charges in there as well, but it's got an excess of negative charges, an excess of electrons. Now here is where we do something to it, and it shows us some incredibly important results. And what we're going to do is I'm going to explain all of this later on, but I'm just going to tell you what happens first. What we do is if we shine some light on here, say we shine some visible light onto the top of this, what we find is that absolutely nothing happens, okay? What is exceptionally important though is if we then increase the intensity of that light, so the same light, same wavelength, same frequency, but we shine a much brighter light onto it, we shine a much brighter light down onto here, still absolutely nothing happens. Now that sounds boring, okay? But what happens now is we take away that visible light and we bring in an ultraviolet light, so higher frequency, shorter wavelength, okay? Now we bring in ultraviolet light and we shine ultraviolet light onto here, and what happens is this gold foil starts to drop, okay? Now that is absolutely crucial, okay? It's we think, what's going on, okay? Surely we're shining light. Surely if we're going to do something with light, okay, an exceptionally bright visible light would surely do just as much as a dim ultraviolet light. But it's not the case. That really, really bright visible light does absolutely nothing, but ultraviolet light, even if it's not very bright at all, can make this gold foil drop, okay? So in other words, it can remove the charges, okay? Now what we're going to talk about today explains these results. Remember, if you want to see this experiment happen, you can wait until we're back into school, or you can click on the link in the description to this video where I will add a link to the Institute of Physics' version of this experiment, okay? So, right, explaining then how does this actually happen? What actually causes it to do? What causes this to happen? And it's all about something called the photoelectric effect, and that is what I'm going to explain today. That's what I'm going to explain today. Now, last time we looked at something called the photon model, and just to remind you, we said that photons of light, okay, have an energy that is equal to the Planck constant multiplied by the frequency, or the Planck constant multiplied by speed of light over the wavelength, hc over lambda. Okay, they're the same thing. Okay, and we looked at all of this last time. Okay, but how do we actually know that light is behaving as a photon? Okay, and this experiment that I introduced just now is actually part of the evidence for light behaving as a photon. Okay, and it's evidence for this thing called the photoelectric effect. Now, what is the photoelectric effect? This is actually something that is incredibly important. Einstein actually got his Nobel Prize for this. It wasn't for E equals mc squared or general relativity. He got his Nobel Prize for what we're looking at today. So it just demonstrates how important it is. Now, if we take our zinc surface, okay, our metal, so it could be any metal, okay, and we shine in some light, we shine photons of light at this surface, we can in some situations see electrons being removed, okay, and these things are called, we call them photoelectrons. There's nothing different between a photoelectron and a normal electron. They're just electrons, but we call them photoelectrons because they are emitted by the photoelectric effect. Okay, now this is the photoelectric effect. It's as simple as that. Light coming in, electrons being emitted from the surface of a metal. That's basically it. But what we need to look at is when it can and can't happen. And what we see that the electrons can only be emitted if these photons of light have a certain amount of energy. I'm going to try and explain that. Imagine the following situation. Now this is an energy diagram as such. If you imagine the electron is trapped inside the metal. Now this electron is down here somewhere. This is not a physical diagram. We've not actually got a physical electron, a ball of electron that is stuck in a little well. It's an energy diagram. Okay. Now, so this electron is trapped by the energy is trapped inside the atom. Now, it requires a certain amount of energy to leave its place. Okay. It requires a certain amount of energy to leave its place in that metal. Now, if a photon of light comes down, okay, and in fact, let's use better colours here. Let's really demonstrate this, okay? Now, if a photon, I'm going to use, rather than visible and ultraviolet, I'm going to use red and blue, just because of the colours that I've got. If a photon of red light comes down, that red light does not have enough energy. That individual photon of light does not have enough energy for that electron to escape from its place, okay? Now, even if you fire more photons down, the amount of energy does not accumulate, okay? The amount of energy does not accumulate in this electron before it can get out. Each individual electron must have enough energy, okay? We see that it does not matter how many photons of red light that I fire down here, not a single one of them is going to have enough energy to remove that electron from here, okay? However, if instead of this, if I have blue light, which we know to be a higher frequency, a shorter wavelength, now suddenly we can say that this photon of light, this one photon of light, has got enough energy to remove this electron from here. Okay, and if I was to shine more photons of blue light down, what would happen is it would mean that more electrons would be able to be emitted. Okay, now the key thing here is that there is obviously a frequency above or below which you can and cannot emit electrons. Okay, you can or cannot emit these photoelectrons. Now this comes to something called this here. Now this here is called the work function. We give this letter here, which is a Greek letter phi. We use the work function. Now the work function is a value of energy. Okay? You could measure it in joules, or you could measure it in electron volts. You could measure it in kilowatt hours if you wanted to. It'd be unlikely you would, but it is an amount of energy, okay? And this amount of energy effectively equates to a certain frequency of light, okay, which we call the threshold frequency. So what you can effectively say is we can say that the work function, okay, is equal to Planck's constant times by the threshold frequency. So if a photon of light comes down with the absolute perfect amount of energy to just emit this electron, okay, then it has the work function of energy and it has the threshold frequency of frequency, okay? So a photon coming in which will just emit this electron, okay, as the work function of energy. And we can therefore define the work function, and it's the definition that you're going to need to know for your exam, and I will write it here for us, okay? I hope that I can fit it in this space. I might have to rub something out. So the work function definition, okay, is the minimum, and the word minimum is absolutely crucial here for your exam, the minimum amount of energy needed to, and the word, we sometimes use emitted, sometimes use liberate, it doesn't really matter at this point, I'm going to use emit. The minimum amount of energy needed to emit, sometimes they say release, an electron from the surface, and this is also important, from the surface of a metal. Okay, so I'll read that again, and I'll stand just out of the way here so you can see it. The minimum amount of energy needed to emit an electron from the surface of a metal. Okay, I'm going to talk you through some of the parts of that. Okay, first of all, okay, the surface part is fairly straightforward. Okay, we're emitting an electron, but this word minimum. Why is that? Now that is because this here is effectively, you can consider the electrons, some of them are going to be in different energy levels within the atom effectively, okay? And this is effectively, we're saying this is an electron that is the closest to being released. Some of them are going to be trapped more deep down, okay? Some of them are going to be trapped closer into the nucleus. And this is, we're saying this is an electron that is the very, the most free of all of the electrons in that metal effectively, okay? So it is the one that's going to be the easiest to release, okay? And therefore, it requires the minimum amount of energy. There could be electrons that require more energy to release them, okay? So, this is the photoelectric effect. Now, if we think back now to our gold leaf electroscope experiment, what this, some of the things that this can tell us, this can explain to us. Now, first of all, we saw that when we shone light, visible light onto it, okay, we saw that there was no change. That meant that there were no electrons being freed from the surface of that zinc plate, okay? So we had our, I'll draw here, okay? Oh, yeah, I'll go with this colour. I don't know how clear this is going to be. So we had loads and loads of negative charges in here, and there were none of them being released, okay? So it stayed where it was. Now, when we used ultraviolet light, clearly the work function or the threshold frequency for zinc is somewhere at the top end of visible light, maybe in the start of ultraviolet, okay? Which meant that for zinc, for that particular metal, visible light does not have the photons of visible light do not have the required energy to emit those electrons. But once you move into ultraviolet, we've gone beyond the threshold frequency, and the photons of light do have the required energy to emit those electrons. So even a dim ultraviolet light will slowly start to emit electrons, okay? If you were to use a higher frequency, not high frequency, if you were to use a higher intensity of ultraviolet light at the same frequency, that just means that you've got more photons of light coming in. So what it means is that you will have electrons being emitted at a higher rate, okay? So effectively, this foil would drop down faster. Now, when you actually do this experiment, it happens pretty much instantaneously anyway, okay? So what I'm going to do now is I'm going to clear this board, and then I'm going to write down some key things that we've effectively that we notice from the photoelectric effect. Okay, we're going to do that, And then I'm going to move on to the second part of this lesson, which is an equation which governs what's going on here. Okay, it's called Einstein's photoelectric effect equation. But first of all, like I said, I'm going to write some summary points which are important lessons learned from the photoelectric effect. Okay, so let's look at these three key points that we've got here. Okay, number one, and I've mentioned this already, photoelectrons are only emitted if the frequency of the incoming photons, of the incoming light, is above the threshold frequency. And remember, the threshold frequency is the frequency that is that gives a photon an energy equal to the work function. Okay, and the work function, remember, is the minimum amount of energy required to emit an electron from the surface of a metal. Okay? Now, number two. Keeping on number one, by the way, before we say this, okay? We have to remember that it doesn't matter how intense the light is, okay? No matter how intense the light is, so in other words, no matter how many photons are coming down here, okay, that's not important. Each individual photon has to have the required energy, okay? Which tells us that there are individual one-to-one interactions. One-to-one interactions is something you're going to be writing a lot in quantum mechanics, okay? So these individual photons have to have enough energy to release this electron here. Each individual one, okay? This is the fundamental evidence for the photon model of light here, okay? Now, secondly, if the frequency is above the threshold frequency, so if we have got light that has enough energy, so we're talking ultraviolet light now, for example, okay? So if the frequency is above the threshold frequency, then emission of photoelectrons is immediate. In other words, there's no build-up. So as soon as some light comes in here, that is of the required energy. So if one photon came in that had the required amount of energy to emit this electron could get emitted, okay? There's no build-up, there's no delay time whilst the energy builds up, lots and lots of photons coming in, building up before this thing gets emitted, okay? Again, it's evidence for this one-to-one interaction, okay? The photon either does or it doesn't have enough energy, okay? Then we've got this here. And this introduces a kind of a new idea. It actually links onto the equation we're going to look at next, this diagram. So if the frequency of the incoming light is greater than the threshold frequency, then increasing the intensity does not increase the kinetic energy of the photoelectrons, okay? What do we mean by the kinetic energy of the photoelectrons, okay? Well, this diagram explains it. I've drawn three possible options. One, this electron does not have enough energy to be emitted. Now, to avoid a slight misconception, if the light comes in and the electron doesn't have enough energy, it's not like the electron tries to come up and then doesn't and falls back down, and then it doesn't interact with that photon, okay? But we can, for the model here, we can picture it this way. So if the photon comes in and it has not enough energy, the electron cannot escape. If the photon comes in and it has just enough energy, the work function, the perfect amount, so if the photon comes in with the perfect amount of energy, okay, you can imagine this electron being emitted, but then effectively it's emitted, it's released, but then it's got no energy, it doesn't go anywhere, it's got no kinetic energy, it's just there, okay? It's literally just got enough energy to escape, but then it's just sitting there doing nothing, okay? More likely is that we're not going to have the perfect amount of energy. The frequency will be greater than the threshold frequency. And what that means is that when this photon comes in, the electron will be emitted, but there will be some leftover energy. And that leftover energy will be the kinetic energy that the electron has, okay? Now, later on, towards the end of year 13, we look at medical physics, we look at X-rays, and when we look at how X-rays interact with matter, we can see that at exceptionally high frequencies, there are different things that go on as well. There's different kinds of scattering where the photon kind of sometimes carries on with a bit less energy, or there's all kinds of different things. But basically, for now, we don't need to worry about that. We're going to consider that the photon effectively disappears. The photon is no more. All of the photon's energy has been transferred to the electron. Some of that energy has been used up to get it out of there, okay? And whatever's left is the kinetic energy of the electron. Now there's an equation that governs this, which we're going to look at in a second. But we're looking at this point here now, and we say that if we are in a position where we have released electrons, okay, we've got a frequency greater than the threshold frequency, then if we increase the intensity, the energy of these electrons does not change. The maximum possible energy does not change, okay? Now that is because by increasing the intensity of the light, remember, we are putting more photons of light down, but each photon doesn't have more light. Each photon doesn't have more energy, okay? So by increasing the intensity of light, more photons come down, you're probably going to be able to release more electrons, okay? So you'll have a greater current, effectively, a greater flow of charge leaving this thing, okay? But the electrons themselves, the individual electrons, will not have more energy, okay? And that's absolutely crucial. Again, it identifies this idea that we are talking individual interactions between individual electrons and individual photons, okay? Evidence for the particle, the photon model of light, okay? Now, I'm going to clear this, and we're going to talk about Einstein's photoelectric effect equation, okay? You quite possibly, in your heads, have already worked out what it is without realizing it yet, okay? So, the equation, HF is equal to the work function plus Ke max. Now, what does this all mean? So first of all, when we think in units, this is actually a fairly straightforward equation, okay? It's actually a very easy equation because everything is just in energy. All this says is just a conservation of energy equation, okay? This basically says that the energy of the incoming photon, okay? I'm not going to write out this in words, actually I will. The energy of the incoming photon is equal to the energy required to release okay, the minimum energy to release the electron, okay, plus the maximum energy, kinetic energy of the released electron. Okay, so basically what we're saying is the photon comes in, it's got a certain amount of energy equal to h, Planck's constant, times by its frequency. However much energy that is some of that energy is going to be used to release the electron. Whatever's left over is the kinetic energy that the electron has. It's as simple as that. And like I said, looking at it now, it seems really obvious, okay? Now, we're going to look at some worked examples of this in a little bit, but I'm going to look at this graph here as well, because it's something that you're going to need to understand. Now, what we've got here is a graph with frequency, so this is the frequency of the photon of light that's coming in, frequency on our x-axis, and the maximum kinetic energy of electrons on the y-axis. Now, the first thing you're going to notice is that it doesn't go through our origin here, okay? Now, this is because what we're saying is that at these frequencies along here, okay, there is no electron being emitted, okay? This is obviously frequencies that give us an energy that is less than the work function, okay? But as soon as you do get an electron emitted, the maximum kinetic energy, okay, is going to increase at a constant rate here, okay? Now, what else can we tell from this graph? Well, what we can do is we can see, because this is energy over here, okay? We can actually, and I'll show you in the y equals mx plus c in a minute, but we can also say that if we follow this down here, we can say that this here is equal to the work function. So this amount of energy on the y-axis here is equal to the work function if you were to trace this down, okay? And we can also say that the gradient of this line is equal to the Planck's constant. Now, let's look at why that is, okay? Let's just look at the equation. Again, you can probably see why this is already. So we'll start with this here, okay? So we've got HF equals work function plus Ke max. Now, what I'm saying here is let's look at what we've got here. We've got Ke max is a y, okay, so we're saying this is y. I'm saying that F is my x, so this is clearly m. So let's just do a little bit of rearranging here. I'm going to bring this over to this side, okay? So we can say that Ke max is equal to HF minus the work function, which is why this is our y-intercept, our value of c in y equals mx plus c. So minus the work function is your y-intercept here, okay? And we can also see that h is our gradient here, okay? So it's a fairly straightforward graph when we think about it. It looks a bit strange, but once you get your head around it, all we're saying is, if I gave you a photon of energy that had a certain frequency, okay, what is the maximum amount of kinetic energy that an electron could have once it's been emitted by the photoelectric effect? Now, if that frequency is less than our threshold frequency, then the answer is 0, because no electron can be emitted. But if the frequency is equal to the threshold frequency, the answer is also 0, because an electron is emitted, but it has no kinetic energy. If the frequency is greater, so it's somewhere over here, then an electron will be emitted with a certain amount of energy, okay, or a certain maximum value of energy. This is a maximum because, for the same reason why in our definition of work function there is the word minimum, okay, because some electrons will require more energy than the work function to be emitted. So we're assuming that we have the most free possible electron, so that exactly the work function is used up to free it, and then all of the remaining energy is used into the kinetic energy. So that's why we use the word max here. Okay, so it's fairly straightforward. I think there's one other thing I'm going to add to this, and then we're going to look at a worked example of how this might work. So the other thing is, we can just say that this would be the graph for a particular metal. Now, we use zinc in the example of the gold leaf electroscope because for zinc, the work function just happens to be a really nice value that shows that visible light does not have the threshold frequency, but ultraviolet light does. So its work function is kind of somewhere in the middle, okay? Different metals are going to have a work function at different places. There might be some metals where red light might have enough energy, but infrared light doesn't. There might be some at the other end, okay? I'm not an expert on that, I don't know all of them, I just know that we use zinc a lot, okay? But other metals would have very, very similar graph, okay? If you had a metal that had a higher work function, because I could see this on a graph, maybe like a 2-mark question, okay? They give you this graph and they say, sketch on this graph a line for a metal with a higher work function. And what you're going to have to do is you are going to sketch a line over here somewhere. It needs to have the same, I'll draw that in a different colour so it's a bit clearer. We're going to draw a line that is over here, okay? It's got exactly the same gradient because the gradient is still the Planck's constant, okay? But it requires more energy before a higher frequency, more energy before it will start emitting. And if you trace it down, you'll notice that it has a higher work function. As simple as that. Okay? The last thing for us to do on this is to look at some worked examples. And I'm just going to do a couple of fairly straightforward ones because there is more that you would need to cover before you can do some of the more complicated worked examples. But I'm going to do one that is a very, very straightforward one, and then one that might link to some other things. Okay? Right. Okay. Now, I've just literally just made this equation up off the top of my head. I'm hoping that the answer is going to be a realistic answer that is less than the speed of light is probably the most important thing. But we'll see how it goes. Okay, I'm going to follow it through, even if it gives me a completely ridiculous answer. Okay. Incidentally, when you do end up with calculations where your answer for a speed is higher than the speed of light, it basically means that part of your calculation you're making an an inappropriate assumption. So you are always, and in this case it's going to be true, you're always gonna, or almost always going to be using the mass of an object. And when something becomes extremely fast, what actually happens is its mass will actually increase. Now, the calculations that I'm going to do are, we're just going to use a constant value of mass. And I think it's going to work out okay. So I think I'm probably just saying something that is not important, but we'll see, okay? Right, let's read the question. A material has a work function of 2.5 electron volts. Okay, so this is a unit of energy. So I'm saying that the work function is 2.5 electron volts. There's going to be a lot of conversions going on. Calculate the maximum speed of a photoelectron emitted by this metal when light of wavelength 120 nanometers is incident. So I'm just going to sketch myself a little diagram because it always just helps. So what I've got here is I've got an electron, okay? I've got some light coming in that has a wavelength of, now I'm just going to write this in meters now, okay? So this is 120 times by 10 to the minus 9 meters. It's obviously 1.2 times 10 to the minus 7, but why do that in our heads really when we can just put 120 and we know this is times 10 to the minus 9 into the calculator and it will solve it for us. Now, so 120 nanometers is the wavelength, okay? So I can equate this to an amount of energy. So I can say that I know that my energy of the photon, okay, and we're just dealing with each individual photon here, is equal to hc over lambda, hf or hc over lambda, same thing, which is equal to 6.63, I'm going to be embarrassed if I get this wrong now, times by 10 to the minus 34, that's my h. I'm just going to write times by speed of light, 3 times by 10 to the 8, and I'm going to put that all over the wavelength, which is 120 times by 10 to the minus 9 meters, okay? So this is going to give me the energy of the photon. Now we're saying this energy of the photon is going to, some of that's going to be used up to free the electron, and some of it's going to go into the kinetic energy of the electron, okay? We know that hf or hc over lambda equals the work function plus the kinetic energy, the maximum kinetic energy, okay? So we need to put our work function in now because I can work out what this is, then I can subtract the work function and it's going to give me the kinetic energy, then I'm going to do a rearrangement of that to work out the speed. So the work function, now this is in electron volts, so I obviously need to convert this into joules because this is going to give me an answer in joules as well. Now, let's do that. So, we'll stick with black. Let's just do this up here. So 2.5 electron volts is 2.5 times by, and I need to times it by 1.6 times 10 to the minus 19. I talked about electron volts in a previous lesson, so I'm not going to go into too much more detail on that. So 2.5 electron volts is 2.5 multiplied by 1.6 times by 10 to the minus 19, and that is going to give me a certain value in joules. So what I could do is I could keep doing this and put it all into one equation at the end once I've done that, but let's do these two and let's find out what our kinetic energy is going to be, so I'm not doing every step at once. So what I'm going to do is I am going to take this here, which I'm going to call number 1, and I'm going to take this here, which I'm going to call number 2, and what I'm going to do is I know this here is number 1 and this here is number 2. So I'm going to do this and I'm going to subtract this. I'm going to put all that into my calculator now, which I will have to get from next door. Okay, so I worked like this, I subtracted this, and I get 1.2575 times by 10 to the minus 18 joules. So that's the amount of energy that my electron is being emitted with, okay? Now, finally, I'm going to rearrange the kinetic energy equation to work out the speed of this electron. We need to know the mass of an electron in kilograms, the rest mass of an electron in kilograms. which by now you probably know. You may or may not. And that is, so the mass of an electron in kilograms is 9.11 times by 10 to the minus 31 kilograms. I'm pulling these out of my head right now, so I'm really hoping that I'm not making an embarrassing mistake. But what we're going to do is we obviously know the kinetic energy equation, which is half times mass times speed squared. So can we see down here? Yes, we just about can. So the speed is going to be equal to the square root of the kinetic energy over half times by the mass. This is my kinetic energy. The mass is that number up there. So I'm going to put that into my calculation now to work out the speed. So, okay, and it gives me quite a nice little answer. So finally, this gives me a speed, and remember this is the maximum possible speed that an electron can be emitted, which is equal to I'll write all the numbers, 1661536.194, 1, 2, 3, 4, 5, 6, so it's 1.7-ish times by 10 to the 6 meters per second, which is a perfectly acceptable answer. It is it's probably about half a percent of the speed of light, so we don't need to worry about any relativistic effects there. Okay, if this answer came up much closer to the speed of light, then we would potentially have to write down, there might be a 1 mark answer that follows that says what is or why isn't your answer perfect, or something like that. But at 1% of the speed of light, there's not a lot of relativistic effects. We're generally going to be fine with that. Okay, so that is a worked example of a photoelectric effect equation. Okay. Okay, so I think this is going to work. I'll just read it out, and then if you want, you've got an opportunity, you can try these questions yourself, and then I will go through the answers. So, a 2 milliwatt laser, a light at a wavelength of 250 nanometers, is incident on a surface with a work function of 3 electron volts. Question A. Show that photoelectrons will be emitted. Question B. Calculate the maximum current created as electrons leave the surface. Okay, so you've got an opportunity now to pause it there and have a go. I will talk you through some of the things that you might want to think about before having a go at the question. So listen to that first if you want a bit of a hint, and then you can have a go, and then I will work through the whole thing as well. So pause now and have a go if you want. So first of all, now in terms of writing these questions, I know that 3 electron volts is somewhere in the visible spectrum, okay? And I know that 250 nanometers is just short of the visible spectrum, so that's somewhere in the ultraviolet. So I'm pretty certain that this is going to work. I really hope it is. In terms of showing that the photoelectrons will be emitted, obviously just saying what I've just said is not good enough. We need to do the calculations. So what you're going to do is you're going to show, it's going to calculate how much energy that is going to give you for a photon. So what's the photon energy if the wavelength is that? You're going to calculate what that is in joules. I mean, what you could do is work out that and then convert it into electron volts, show that it's more than 3. Or you work out that in joules, you work out that in joules and show that that is bigger than that. Okay, that's what we're going to do for part A. Calculate the maximum current created as electrons leave the surface. Now, I was tempted to make some kind of question a reverse of the previous one where we're working out the work function, but I thought this would be a little bit more interesting. Now, in doing this, what we're going to do is we need to think about this idea of one-to-one interactions. So in a perfect world, now this is never going to happen, but in a perfect world where every photon of light comes in, emits 1 electron, so every single photon is able to emit an electron, okay? What we're going to be doing is we're going to be working out how many photons, okay, are going to give us now this is millijoules in each second, isn't it? Okay, so 2 millijoules, how many photons at this wavelength are going to give us 2 millijoules, okay? And that number of photons we're going to assume in the maximum world, okay, is going to give us the same number of electrons being emitted. Then we can work out what that is in coulombs, and that's the amount of coulombs in a second, because that's the amount of joules in a second. So that gives us the current in amps. So it should work out like that. Okay, so feel free to have a go at that. Now I've given you the instructions effectively. I'm now going to work through the answers, and that will be the last thing that I'm looking at in today's session. So, part A, show that the photoelectrons will be emitted. So the way I'm going to do this is I am going to, because I'm going to need these things in joules anyway, I'm going to work out what this is in joules, and I'm going to convert that into joules. So, E energy equals to HF or HC over lambda. So this is 6.63 times by 10 to the minus 34 h times by speed of light 3 times by 10 to the 8, okay, meters per second, all over the wavelength, which is 250 times by 10 to the minus 9. Yes, I know that's 2.5 times 10 to the minus 7, but I don't bother typing in like that. So 6.63 times 10 to the minus 30. Yeah, it's going to work. This gives me equal to 7.956 times by 10 to the minus 19. Okay, joules. Now I'm going to work out what 3 electron volts is in joules. So 3 electron volts equals 3 multiplied by 1.6 times by 10 to the minus 19 equals 3 multiplied by 1.6 times 10 to the minus 19. Happy, yeah. 4.8 times 10 to the minus 19. 4.8 times by 10 to the minus 19. So, joules. And I can clearly see that the energy of the photon is greater than the work function, okay? Therefore, photoelectrons can be emitted. And they're going to be emitted with a kinetic energy, or a maximum kinetic energy, equal to the difference between those two numbers. If I wanted to, I could then work out the speed of the electrons, all kinds of things, but I'm not going to do that today because that's not what the question is asking. Okay, part 2. So we know that they are being emitted. At this point, I'm not interested in the work function anymore. I'm only interested in this number here. So I'm going to rub out this bit. So part 2, what is the maximum current, the rate of these electrons being emitted basically? Now I know that that is the energy of each photon. I've just worked that out. So how many of those are being directed per second in order to give me this? So what I'm going to do is I'm going to say 2 times by 10 to the minus 3 joules per second, okay, divided by this number here, 7.956 times by 10 to the minus 19 joules, is going to give me a number of photons per second, okay? It's going to give me, and let's type this in, so 2 times 10 to the minus 3 over 7.956 times 10 to the minus 19 is 2.513826 dot 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 dot. So 2.5 times by 10 to the 15, and the units here effectively are per second, second to the minus 1. Okay, so 2.5 times 10 to the 15 photons per second is what is required at that frequency to create this power. Okay, sometimes they might make these questions harder, might do an intensity and an area, it just adds tiers to it, but I've not done that. So this is the number of photons per second, okay? It's per second. Now what I'm saying is that in this dream world where every single photon interacts with an electron and therefore can emit an electron, we're going to say that the number of electrons emitted per second is equal to this, okay? So often in questions you get, instead of saying this, they might give you a percentage, they might say a certain percentage of the photons interact with electrons, but I've not done that. So this is the number of electrons emitted per second because it is the number of photons incident per second. We know that each electron has a charge of 1.6 times 10 to the minus 19 coulombs. So I'm going to multiply this by 1.6 times 10 to the minus 19, and that's going to give me an amount of charge per second, amount of coulombs per second, in other words, a number of amps. So, have I got space at the bottom? I think I just about can fit it here. So I'm going to take this number, and I'm going to times by 1.6 times by 10 to the minus 19, and it is going to give me times 1.6 times 10 to the minus 19 equals 4.02212, something like that. So basically 4.0 times 10 to the minus 4. 4.0 times by 10 to the minus 4 amps, coulombs per second. And that is our answer. Okay, it's, I'll say as simple as that. You may or may not agree with me that it's simple. But that is how we would work through this. Now, one thing that you might notice here is that I've done a lot of timesing by 1.6 times 10 to the minus 19, dividing by 1.6 times 10 to the minus 19. Often in physics, if we leave things in units like electron volts, we can actually simplify things by not having to multiply by factors and divide by the same factor later on. But to make things simple, certainly when we're starting out, when you're getting used to something, you really want to be putting everything into a unit that we can understand and deal with. And therefore, that's why every single thing, what I've done here, everything I've converted into joules. So I've converted everything into joules. I converted this in, kept turning that into joules, I kept it as joules, done it all in those kind of units, just to avoid trying to take shortcuts and ending up making mistakes that way, okay? There will almost certainly be some simplifications, but this is the most fundamental way of doing it, okay? That's it for today. Next time we're going to be looking at, I think it's wave-particle duality. Wave-particle duality is, we've looked today at evidence for light behaving as a photon, light behaving as a particle, whereas in the past we have looked at light generally as a wave. So you might have seen the Young's double slit experiment and diffraction, which is the wave evidence of light. We've looked at the particle evidence of light today. What we're going to do next time is we're actually going to be looking at matter, so things like electrons, and show that whilst electrons in the past we've considered to be particles, we can actually sometimes consider them to be a wave. So it's kind of the opposite. With light, we've always learned it as a wave, and now I'm telling you it's a particle, but it's actually still a wave, but it is a particle, it's a bit of both. Well, we've always looked at electrons to be particles, and next time I'm going to tell you how actually they behave like waves, okay? Hopefully that's not confused everything for you and keeps you interested. I will see you next time. Thank you.